Within this slide, we are going to deduct the mathematical matrix and scalar equations of the Clarke transformation needed for the conversation between the three-phase A, B, C and two-phase XY coordinate systems. In this video, we are going to assume that the measured phase currents are the three-phase symmetrical sinusoidal signals. The latter assumption means that we can neglect the need of filtering the measured phase current signals because no upper harmonics are present in them. However, we are going to implement a low-pass filter during the function software development part. So, all the necessary part of the FOC algorithm is going to be covered altogether. In the current slide, you can see the relevant block representation of the Clarke transformation. In the next video, you are going to understand why is it marked with a 2/3 as well. You can see the mathematical representation of the Clarke transformation on the slide. As you may notice, the XY coordinate system is represented in the complex plane. The transformed current component in the x direction is the real part, and the current component in the y direction is the imaginary part of the synthesized stator current. The stator current can be calculated as the vectorial sum of the three-phase individual phase currents in the appropriate directions. Previously, we have talked about how the stator current vector can be represented within the ABC coordinate system. If you're not sure how is it done, check out slide 22 in the video series. For a quick reminder, the individual phase currents can be interpreted in the XY complex coordinate system with algebraic equations. After we have synthesized the resulting stator current in the XY coordinate system, the x direction can be interpreted as the real and the y direction can be interpreted as the imaginary part of the latter mentioned current vector, which means that in case of the current vector in the x direction, if you omit the imaginary parts of the equation and carry out the necessary multiplication remaining, you are going to get the scalar equation in the bottom part of the slide interpreted for the x current component. The same conclusion can be taken if one obtained the current in the y direction. In this case, if you omit the real parts of the complex numbers and carry out the necessary multiplications remaining, you are going to get the scalar equation in the bottom interpreted for the y current component. In the picture, you can see the symmetrical three-phase coordinate system represented with A, B, and C axis, as well as the two-phase imaginary coordinate system marked with XY axis. As you may notice, the red vector is representing the resulting stator current vector that we have just described in both aforementioned coordinate systems. Let's move on and simply introduce the matrix operation of the Clarke transformation as part of the field-oriented control algorithm. As we have seen in the previous slide, it is relatively easy to mathematically describe the resulting stator current vector in the three-phase coordinate system. During the matrix representations of the Clarke transformation, we are collecting the necessary color equations into a matrix equations. If you watch closely, by utilizing the row-column multiplication technique, we can easily determine the scalar equation of the x and y current components based on the three-phase currents. There is a new zero component in this matrix representation, which we have not clarified yet. The zero current vector component shall be zero in case of a pure symmetrical three-phase current system. However, when the measured phase currents are being distorted and the delta connection is used in case of a PMSM motor, it is possible to measure such zero current that is circulating inside the phase windings without useful torque production. Later, we will see that this information will be lost during the Clarke-Park transformation methods, since the Park transformations only inputs are the currents in the x and y directions. This zero current component information can be used, however, for the safety-related mechanism to identify when such event arises. The previously deducted mathematical representation of the Clarke transformation can be further simplified if we assume that the sum of the three-phase symmetrical phase currents are equal to zero. In this case, the scalar equations can be used to perform the coordinate transformation between the three-phase and two-phase systems. As you may notice, in the simplified Clarke transformation, it is sufficient to measure only two-phase currents at a time, which means that in those systems where it is guaranteed that no zero-order current component will flow, we can spare the cost of one-phase current measurement. Of course, it is wise to give the developed system a little redundancy to make it safer and more reliable. All in all, we have deducted the necessary scalar equations describing the Clarke transformation method as part of the FOC algorithm. Now, we have two simple equations that can be programmed with ease in MATLAB Simulink and spare a few clock cycles for our microcontroller to operate more efficiently compared to the matrix representation of the transformation algorithm. In the next video, we are going to introduce the Clarke transformation. I hope that you're enjoying the course. Remember to give any feedback you wish or contact me if you have any further questions regarding these topics.